Imagine a material that conducts electricity with zero resistance forever. That is the holy grail of physics, and for decades, it has been stuck in the lab because finding these materials takes centuries. Today, we are changing that story completely. Scientists have just cracked the code by combining machine learning with quantum physics to discover new superconductors at a fraction of the time used before. We will dive deep into how algorithms are now acting as superscientists, filtering through millions of possibilities in minutes instead of months, and what this means for your future electric cars, grid power, and even everyday electronics. Let's talk about the problem we are solving. You know how electricity flows through copper wires? It gets hot. That heat is wasted energy, which is why our power grids lose a massive amount of energy just getting from the plant to your house. Superconductors change all that. They allow electricity to flow without any resistance at all. No heat, no loss, infinite efficiency. The catch has always been temperature. Most superconductors need to be cooled down to near absolute zero using liquid helium, which is expensive and hard to handle. We are talking about room temperature superconductors here. If we could make them stable at room temp, we would revolutionize transportation with maglev trains that glide effortlessly, power cities without waste, and shrink the size of computers exponentially. For a long time, finding these materials felt like looking for a needle in a haystack, where the haystack was literally the entire periodic table combined with billions of chemical combinations. It was slow, tedious, and often gave up before it found anything promising. Here is where things get interesting because the game has changed entirely. Researchers have discovered that we don't need to guess anymore. We can use artificial intelligence to screen materials at a speed that was previously impossible. A recent study published in the journal Newton showed that using AI, scientists can now identify complex quantum phases in materials in just minutes. Before this breakthrough, identifying these same quantum states took researchers months of painstaking laboratory work and theoretical modeling. The new method uses an improvised database built with machine learning frameworks to predict superconductivity based on descriptors motivated from quantum self-dual theories. By applying a supervised learning model like random forest, they can predict the critical temperature as a function of various material properties. This isn't just simulation. It is an active screening method that has already led to the discovery of 2 new superconductors. It acts as a digital filter that instantly rules out the thousands of combinations that won't work, leaving only the viable candidates for real-world testing. Why does this speed matter so much? Because in science, time is everything. In materials science, the gap between hypothesis and discovery used to be years long. Researchers would spend months running simulations or growing crystals just to see if a slight change in pressure or composition would yield a superconducting state. This new approach shortens that timeline from months down to minutes. It allows researchers to iterate through hundreds of potential candidates almost instantly. Think about the implications for low-dimensional superconductors, which are particularly tricky to study due to their complex quantum behaviors. With this tool, we can explore the vast landscape of quantum phases without getting bogged down by physical limitations in the lab. The technique described recently combines machine learning with quantum physics to create a much faster way to search for many more materials. This acceleration means that scientists are no longer waiting for luck or serendipity to strike after years of work. We can now systematically hunt for room temperature superconductors and other exotic states that were previously thought to be too rare to find. It turns the search into a targeted expedition rather than a blind search. So, what does this actually mean for us in the real world? If you are thinking about electric vehicles, the battery technology could evolve to store and move energy with near-zero loss, drastically increasing range and safety. For your home, smart grids powered by room temperature superconductors would stabilize voltage spikes that currently damage appliances and waste millions of dollars annually. The ability to synthesize these materials quickly means that we can customize them for specific needs. Maybe one version works best in a high-speed train engine, while another is optimized for long-distance power transmission lines. The fact that this method has already yielded 2 new superconductors proves the path forward is open. We are moving from an era of waiting to an era of engineering solutions at light speed. this isn't just about making one better material. It is about creating a library of materials we can design on demand. It paves the way for quantum computers that run cooler and more efficiently, medical imaging devices that become portable and affordable, and a global energy grid that finally makes sense. The future of physics is being written line by line in code right now. We are standing at the threshold of a new era where materials science meets artificial intelligence. By speeding up our discovery process from months to minutes, we unlock the potential for zero-loss electricity and technologies that were once science fiction. The tools we have now allow us to hunt down superconductors with the precision of a laser guide rather than the sweep of a net. If you found this breakdown of how machine learning is reshaping physics fascinating, please hit that subscribe button so you don't miss our next deep dive into the future of technology. Drop a comment below telling me which application excites you most, electric cars or smarter grids, and let's start a conversation about what comes next in this rapidly evolving field.